Now we can also look at the size of an ion, and we can look at that relative to the parent atom. So for example, when we're looking at sodium, we can say, well, what happens when we go to sodium plus? Or if we look at chlorine, what happens when we go to chlorine minus? And what we see in all of these cases is that anions are larger than their parent atom. So Cl minus is going to be larger than Cl, but cations are smaller than their parent atom. And so sodium is going to be larger than Na plus. And when we look at why this is happening, we can see this is also due to Coulomb's law, to that charge, that attractive force between the nucleus and that outermost electron. So let's look at sodium first. When we have a neutral sodium atom, what we have are 11 protons and 11 electrons. When we go to the ion, now we have sodium plus, so we still have 11 protons because it's still sodium, but now we have only 10 electrons. So now the force being exerted on each of those electrons is a little bit greater. So think of it this way. Imagine that you're trying to keep up with a large group of kids. So say there's 3 kids and there's one of you. You only have 2 hands, and you're doing your best to keep them close to you, but you only have 2 hands and there are 3 of them, so they're kind of moving away and getting away from you a little bit. But now one of them goes home, and now it's you with 2 hands and 2 kids. You're going to have a stronger attractive force to those 2. You're going to be able to keep them closer to you because it's a more manageable amount. And so each kid is going to feel a greater force of you pulling on them with your hands. On the flip side of that, if we look at chlorine, and so when we look at chlorine, what we see happening is that we have 17 electrons in chlorine with our 17 protons. When I go to Cl minus, I have 18 electrons with 17 protons. And as a result, it's going to be a little bit harder for each of those protons to have that same attractive force towards the electrons. And so now we can imagine having 2 hands and 2 kids to hold on to, and then suddenly we have 3 kids to hold on to with our 2 hands, and what we're going to see is we're not going to be able to keep them as close. And so the same thing's happening with our ions, that we look at sodium and it goes a cation, so we have same number of protons, same positive charge, less negative charge. So each electron is feeling more than its regular share of that nuclear charge. And just the opposite with the chlorine. When we gain that electron, now each proton is having to kind of divvy up its attractive force a little bit, and so it's not each giving the full effective charge towards each of those electrons. So here we see the same diagram we were looking at before, and what we want to notice here is what's happening, the kind of comparison between the neutral atom and its ion. So notice we've got all these red lines are representing the neutral atom to the cations. So beryllium is getting smaller, sodium is getting smaller. We also see a trend with the oxygen getting larger as it goes to O2 minus. Fluorine gets larger as it forms F minus. Chlorine. We still see the same trend between fluoride and chloride as we do between fluorine and chlorine, that fluoride is smaller than chloride because we still have the issue of the electrons in fluoride are in the N equals 2 level, and with the chlorine we're going up to the N equals 3 level. So within the ions we see the same trend that we saw in the atoms, but we're going to see that all of the anions are bigger than their parent atom.